So let's begin. We're a little behind. We need to catch up. Are there any questions on the homework?
Yes.
Okay.
I think it's problem 5 on the It's either 5 or 4.
Okay.
Or 5 or 6. Can I repeat? 7.3, number 14.
Number 14?
Yeah.
All right, since that one's specifically look at that first. So it's just finding the formula for the nth partial sum?
Yeah. The answer, second part of it, second term had 5 over the square root of n plus 3 plus 5 over the square root of n plus 4. But in the original series that they give you, the denominator has the square root of k plus 2. The second one has denominator has square root of k plus 4.
Okay, so it's slightly different.
Yes, I don't know how they got to 3 and 4.
So they had 5, say that again, 5 over root k plus 2?
So the final answer, that's the second part of the final answer. The first part is 5 square root 3 over 3. You don't get the iteration of the problem.
Yeah, I was trying to see if what your problem was, so I could just write that.
Okay, yeah, it was here. The problem is sum, what is going to be 5 over square root of k plus 2 minus 5 over the square root of k plus 2.
So they do tell you it's telescoping, so we're going to look at the first few terms when k is 1. I'm not sure how far we want to go here. Maybe that's enough. I don't know. All right, so let's see what cancels with this. All right, so the 5 over root 5 cancels here. So I'll just say, let's just write this out. The second cancels with the first term, that is 2 to the left. I suppose we could backtrack and say the first cancels with the second 2 to the right. 2 to the right here. It's 2 to the left. Okay, so the 5 over root 3 wouldn't cancel. There's nothing to the left, so we're still going to have this term. The 5 over root 4 wouldn't cancel because there's not a second term to the, or second pair, rather, to the left. How about the minus 5 over root 6? Would that cancel? This minus 5 over root 6, would that cancel with anything? Yeah, eventually. So it's going to just cancel over here with this next term that we didn't write out. So that's gone. That cancels with this. The minus 5 over root 7 cancel. Yeah, with, again, 2 more to the left. So here, that one. Well, so we might need to write a couple more of these out. But the nth term, the 5 over root n plus 2, does that cancel with anything? Yeah. That'll cancel back here. And then the minus 5 over root n plus 4 cancel with anything? No. So would everything else cancel? Okay. So we're good with that. Our nth term is these 3 terms that we've ended up with here. Sorry, our nth partial sum, not nth term. Nth partial sum is 5 over root 3 plus 5 over root 4 or 5 over 2 minus 5 over root n plus 4.
They have some term in there. So they have minus 5 over square root of n plus 3 plus 5 over the square root of n plus 4.
N plus 3.
Yeah.
So let's come over here. That would have been this term. It's this. Yeah, so does that make sense to have that term in there? This second term in the pair cancels with the first term that's 1 to the right. Or sorry, 2 to the right. There is nothing on the right of the nth term. So that term right there would also remain. So you just got to be careful. I would always recommend writing out at least the first 3 terms and the nth minus 1 and n minus 2 term. Usually that's enough to cover things that have multiple terms that don't cancel. Okay. You know, and honestly, it would have been just a happy coincidence if you would have missed that. It's still not going to affect the sum, right? Because any of these terms that are left over are approaching 0 as it approaches infinity. So even if you would have, you might have gotten dinged for like not expressing the nth partial sum correctly, but your overall sum of that series still would have been correct, just by coincidence.
The 5 over square root n plus 1, that would have canceled.
Yeah,
and
so
that
that's
second one would not have, because
right.
there's nothing to.
Yeah, exactly. So this term cancels with this term that's 2 to the left. Okay, so there's our nth partial sum, and the sum of the series. I don't want to write that series down again. Sum of the series is the limit as n goes to infinity on the partial sum. So that's, maybe they want you to combine like, get a common denominator, but that is the sum of that series. Do you have any questions on that? Do that one, Trey? That was number 4. Okay, so use the integral test or state that the test does not apply. So what were the conditions on the integral test? Continuous, positive, and what? And decreasing, right? All right, so first we've got to determine if we look at f of x equals to 1 over square root of x plus 3. If we look at that as, is it a continuous positive decreasing function? Remember, this 4 is a constant. So the 4 is, you can think about this as being 1. And really, we're just trying to determine what this series does. Because if it diverges, multiplying by 4 still diverges. If it converges, multiplying by 4 still diverges. If you want to include that into your function, with your function, then that's fine too. Okay, so is it continuous for all x larger than or equal to 0? Yeah. So the square root of x minus 3 is only undefined from values that are less than -3, right? -4, et cetera, et cetera.
Less than or equal to Less than or equal.
Yeah, less than or equal. Well, yeah, if it's equal to -3, then you've got the square root of 0 on the bottom, which you can't do, so yeah. Is this function positive for x values that are larger than or equal to 0? Yeah, so those are pretty. Usually the easier of the two to determine. Is the function decreasing? Yeah, so we know there's positive terms. We can either look at f prime, or if we just look at what the terms are actually doing. The limit as x goes to infinity on this function, approaching 0, and they're positive, so that means they have to be decreasing. So we'll just say yes. Okay, so our integral test is going to start off as the integral from where to where? Yeah, 0 to infinity. Remember, the lower bound of your integral test matches the index where you start on your series. Huh? Yeah. So we can do that. You can do that right now if you want. There's a really a preferred order to that. And our function 1 over root x plus 3 dx. Okay, how do we evaluate that integral? U substitution, so that means u equals to what? We can do x plus 3. Du is dx. Remember to, if you're using a U substitution or integration by parts here, I would just find the full-on antiderivative in terms of the original variable x, and then replug all that stuff back in to compute this limit. I wouldn't worry about trying to change these bounds and making that problem harder than it needs to be. So we have, really we're just going to look at the integral without any bounds right now. So I'm just going to do this. And not even worry about this limit right now. So that's u to the negative 1/2 du. Yeah. And the antiderivative of that gives us what?
So negative 2 square root of
Yeah. U plus 2. Say that again?
negative 2 times the square root of x plus 2.
Oh, just be two. Yes, right.
Oh, it's positive 2.
Okay, yeah.
Which
Positive
would be
2?
positive.
Yeah, because you're gonna add 1 divided by 1/2, so it's positive 2. And here again, since we're gonna plug in bounds eventually, I wouldn't worry about the constant either. So just that's our antiderivative. That gives us the function of x. So then I would just start here with that again. No, I don't know. Just put this 2 up here.
So you got to pull out. Remember that.
Oh yeah, the 4 is not going to affect convergence or divergence, so we're not even going to worry about it. If you want to put it in there, you totally can. It doesn't matter.
Integrating it again?
Oh yeah, we're not.
Right.
Just kidding. Okay, so will that converge or diverge?
Yeah, bounds don't really change, right?
Uh-uh. Yeah, sort of. Again, that 2 is kind of like a constant. If this thing is finite, multiplying it by 2 is not going to change the finiteness. If this thing's infinite, multiplying by that 2 is not going to change that either. But we should just to be technical, yeah, we should have that there. So we're not confused. But this is infinity minus root 3 times 2, still infinity. So since the integral diverges, what does the series do? Series also diverges. Whatever this was. 0 to infinity or 4 over.
What are those 3 dots mean?
Therefore, what was that? 4 over square root, yeah, converges or diverges. I guess if you had that 4 in here, the only difference would be that it's an 8 instead of a 2. Questions on that? Yeah, you could leave the 4 in there. See if we left that 4 here, then this is a 4. That 4 gets factored out of this. That 2 multiplies that 4, and then that's an 8 instead of a 2.
Yeah, we'll just have to tell them.
Oh, okay. Yeah. Any other questions? where were we? Finish that. Oh, we weren't very far then, huh?
Yeah, we just started page.
We just do that one?
Yeah, we're on number 2.
That one? Weird. I thought we got further than that last week.
That's where we got some.
So that was the direct comparison?
Yes.
Okay, sure. Did we actually talk about that at all, or? I know we started it, okay. I had a typo, that should start at k equals 4, not k equals 1. So the idea of the direct comparison test was to choose a series sort of as, thinking about it as like a limit as k or n approaches infinity. So that's why we just looked at 2 over root k squared, ignoring all the other negligible terms in the numerator and denominator, which gives us 2 over k, which we know that's 2 times our harmonic series, so that's a divergent series. So you'll notice that if whether we include that 2 or not doesn't affect our comparison, and it doesn't affect the conclusion. So we could have just equivalently compared this to 1 over root k squared or 1 over k. All right, once we've found the series to compare with, what do we have to establish?
It's going to be greater.
Right, we have to establish a relationship between the series we're comparing versus the series we're given. And again, keeping in mind that we know 2 over k is the series, but it's easier to compare to the equivalent form 2 over root k squared. So is it easy enough to choose which one's larger than or which one's smaller than? Yeah, which one of these is smaller? This one's smaller, we're subtracting 3 on the bottom. Do y'all agree with that? So maybe you can start off with, if you're unsure, just start off with k squared minus 3 versus k squared. Well, clearly k squared is larger. We take the square root, it doesn't change. But we need to look at the reciprocal. So when we reciprocate, we have to change the inequality. Minus 3 over root k squared. Do what?
The 22nd is bigger than 50.
Sure, yeah. And then multiply both sides by 2 doesn't really change that. Yeah, because the numerator's small, or the denominator's smaller, so the fraction's bigger. So the series we're given is larger than this series. Let's write this out. This series is larger than our divergent series. Which again, that's 2 over 10. What are our bounds? 4 to infinity. So what does this tell us? Yeah. So it tells us what we're looking at is we're trying to answer a question about a series that's larger than a divergent series. So if the series is larger than a divergent series, it has to diverge as well.
Here's how you got that it's larger.
Say what?
You say
just summarize with the given series. Is larger than a divergent series. Do y'all have questions? No? Okay. Okay. I don't mind if y'all are talking, but it's totally weird, which means other people. Larger than a divergent series. Which means it also diverges. Any questions on that or that test at all? I think that's our last example for that one. So honestly, I think once we start looking at the limit comparison and the root and ratio tests in 10.7, like that stuff is really easy to get confused. I think up till now, the tests are pretty clear cut, but there are a few tests that have similar criteria. And it's sometimes I see students mixing those up. So I think we're good until now, and then we start seeing the limit comparison and then the two tests in 10.7 have a tendency to get a little mixed up. Which, by the way, our schedule says that we're going to cover 10.5 and then 10.7, but we'll actually go in order. We'll cover 10.5 and then 10.6. All right. So the next comparison test is the limit comparison test, and usually this is preferred or utilized over a direct comparison test. And what it says is that we've got two series again, comparing the two. Just like in that direct comparison test, this A sub k will be the given series, and our B sub k, we'll pick this one. And again, we're choosing that series B sub k. Preferably, it's a series that we know something about. We don't know whether the chosen series converges or diverges. It doesn't help us perform these tests. Okay, what we're comparing now is the limit at infinity of the A sub k terms over the B sub k terms. All right, and calling that limit L, and then there's three conditions. If L is finite and not zero, then both of those series do the same thing. So if we chose a convergent series and we got a finite limit not zero, then it's a convergent series. If we chose a divergent series, finite number not zero, then the given series diverges. If the L is equal to zero and the chosen series converges, then we can say the given series converges. If the limit is infinite and the chosen series diverges, then A sub k diverges. If you think about these things maybe in terms of like that limit of A over B equaling a finite number, zero, or infinity, maybe that the conclusion for those three cases makes a little more sense. I don't have enough space to write it out. I'll write it out here though. If this is equal to zero, as what do we know about A versus B? Yeah. If that limit is infinity, what do we know? Yeah, A grows faster. And we didn't really, as far as growth rates go, we didn't really talk about what happens if it's some finite number, but that just means their growth rates are comparable.
it's none of those, it's just inconclusive. Or what would you want to say?
Yeah, finite number, 0 or infinity.
Can't be negative.
Yeah, because we're only dealing with the series that have positive terms.
If both of the series converge to zero, is that a special case where it would be, or is it just zero?
You mean like in the sense right here, if it's 0 over 0?
Yeah.
Yeah, then the L'Hopital's thing would be, we don't really encounter those, I don't think. We would look at this in the sense that it's, let's see how these usually arise where both A and B, the series are quotients in and of themselves. So like how we utilize this in practice is typically, we take A multiplied by the reciprocal of B. So we can have two, yeah, right. Okay, so notice this, the first condition, if this limit is 0, then B grows faster. So that's leading us to scenario 2. Really the only conclusion we can make is that if B is growing faster than A, but B converges, what that means is basically B is converging faster than A is converging. Okay, if it's this scenario, A grows faster, but in this conclusion, B sub k diverges. So this is saying that A grows faster than a divergent series. Does that make sense that it diverges then? And if they grow at comparable rates, and whatever B sub k converges, then A sub k is comparable to B, so it converges. If B sub k diverges, then A is still comparable to that, which makes it diverge. So that's kind of the justification behind this theorem. Let me see. Yeah, this theorem is proved in your textbook, and then they use the epsilon delta definition of a limit to prove that. It's actually a pretty short proof if you're curious, maybe a little more how that works. Let me try to link this up here. So this is our limit here, and our conditions here. So let's come back to this example. I think it's a little bit more involved, not much. But let's start with example 4, just to kind of see what the limit comparison does. It's just like the direct comparison. The first thing we want to do is identify the series we know something about that's the most closely related to the given series. So really, the first step is still to pick this series. What do we want to choose here? Yeah, we want to choose 1 over 2 to the k. What do we know about this series? It's geometric, and it converges, yeah. Then the second step is to compute the limit. So it's the limit as k approaches infinity of a sub k was the given series over the chosen series. Sorry, the terms of the series rather. So like I said, in practice, what that equates to is just taking A and multiplying by the reciprocal of B. So to evaluate this limit. What is that limit? Yeah. How do we know it's 1? Yeah, and then you would do, if you're going to look at it like that, then you would do L'Hopital's rule, which is fine. But the -5 makes no difference, right?
Yeah.
2 to an extremely large number minus 5 is 2 to an extremely large number. So really, this is limit at infinity is equivalent to just the limit as k approaches infinity of 2 to the k over 2 to the k. Which is well, I guess technically they were calling this L. So L is equal to 1. What's our conclusion? You got a finite number that's not 0, then both of those series that do the same thing. So L equals 1. Same thing, it seems weird. So this series converges. By the limit comparison test.
We got to. Essentially, it's a finite number that, one approaches the same carry, approaches three. It's convergent.
Right. Yeah. So so we know that this limit of a over b is equal to 1. So that is the L is finite positive number. Then the series either both converge or they both diverge. And since we chose this to compare to as a convergent geometric series, then that's why A converges. Did y'all have any questions about that? So, like if we were to use a direct comparison here, there are different criteria, but for something like this, the direct comparison is sort of somewhat easier to establish, right? Because we know in comparison, 1 over 2 to the k minus 5 is greater than 1 over 2 to the k. But oftentimes, for the limit comparison test, you can see the superiority of the limit comparison test is in a series like example number 3. So I don't know about you, I definitely wouldn't want to try to establish a relationship between that and the series that I'm comparing with.
Is it similar, determine whether finite is infinity or 0? If it goes to 0, does that mean it's inconclusive? It's almost like the divergent test.
If your limit goes to 0, it's only inconclusive if the chosen series diverges. If the chosen series converges and the limit is 0, then A converges. Yeah.
We also need to know if this series converges by looking at the power of the leading terms and the numerator and the denominator. Because it seems that the power of the denominator is higher than that in the numerator.
Which means as far as the limit is concerned, what would happen? It would go to 0. So then you're utilizing what test? Divergence test. So if the divergence test is 0, what does that tell us? It's inconclusive, right? Right. So the divergence test here is inconclusive. What do we want to compare with? Which would be what power? We're just going to look at, just think about leading term versus leading term. We can simplify this. our threes divide out, we have k over k to the 1/2 times k to the first, which is k to the 3/2. Yeah.
So you would just not care about the -5 to k?
No, because the test has us taking the limit as k goes to infinity.
It's less than
And it's not just k, it's in a sense. We have to distribute square root of k through.
Right. Yeah, so the square root of k minus 5 times the square root of k compared to 3 to the 3 times k to the 3/2. You know, the 1/2 power versus 3/2 power in the sense of an infinite thing, 3/2 power is totally dominant.
Okay.
Sorry, did you have something to
Yeah,
add?
you just cancel out the k's altogether.
Yeah. Yeah, so we're comparing this to 1 over. I mean, you don't have to write all of this. I'm just really showing you like the logic behind how you typically choose a series you're comparing to. So that's k to the, or let's just write it as this. Yeah, just divide the 3k's out. Okay, so that's what we're comparing to. What do we know about the series 1 over k to the 1/2? Not geometric because it's not like 1/2 to the k.
It's a p series.
It's a p series, right?
So if k is less than 1, it's
I don't remember. It's divergent. So it's less than 1, which means it diverges. All right, so the known series we're dealing with, comparing to, is a divergent series. Then we're going to compute L as the limit k approaches infinity. We have our given series, A, write this out, 3k to the 3/2 minus 5k. So there's A divided by B, we'll multiply by the reciprocal of B. So what is that limit equal to? Huh? No, because this is k to the 1/2 times all of this stuff up top. So let's just, that's 3k to the 3/2.
Don't those k to the 1/2 just cancel out?
Where?
Before you expanded it out
Yeah,
on the
it's
bottom.
very expanded.
On the bottom.
Yeah.
Oh yeah, they would.
That's what
But it's too late for that. If that, I mean, that is easier to see. I just wanted to show you this way. You get the same thing, but we're looking again at the leading term over the leading term, right? It doesn't really matter if this is a fractional power. If, like in the last example we saw, it was exponential, like 2 to the k. Doesn't matter what it is really. So this is equivalent to this limit. I'm not intentionally trying to do this in a confusing way. I just, sometimes it's helpful to see things in a different way. Well, But you're right, if we would have just left that root k here instead of multiplying that in, then that root k that's sitting out here would have canceled with that. So the L again is equal to 1, and that means our conclusion is what? Yeah, if both series do the same thing, since what we compare to diverges, given series diverges as well.
Are we gonna be handling many cases where this test is inclusive?
No, that's why it's preferred over the direct comparison. Not only is it easier to just compute the limit of two things that are divided, as opposed to establish some sort of less than, greater than connection, but this is, in general, it's, you end up with a situation where it's not inconclusive as much as a direct comparison. Okay, any other questions on this test? I think we may have one more example. This is, all right, why don't you all try example 5.
No.
Tim, goodbye forever. I miss you. Yeah. That's all right.
That'll be the same thing.
So this one's a lot more involved than the last two we've done.
And then they. Like, he does the biggie. Have you ever? There's also that. Patrick's also. Patrick was good. Patrick helped me keep track of this.
Find out, or
Would you
Later.
compare?
Yeah. The sum and that sum. So, do you know anything about cable?
Yeah, why would you?
well,
Is there a way to find out? Yeah.
now you gotta figure out how to test this thing for
Divergence. That's like a separate part of the problem.
All right.
Because then once you know if this thing converges with divergence, then you can establish the serendipity.
Yeah.
Okay.
We're trying to find out whether it's at
Yeah, actually.
So, my second day of the verify, I kind of left it in the test.
Oh,
It went to zero. Then I went
Put it back on.
So you guys just took the natural laws on the whole thing, and that's the elements of it minus the element.
Written anything, but that's where my brain is
I'm assuming.
Right, so K was 1/5, and then what I'm saying is include it in that form. Isn't that necessary?
Yeah.
You just put it in.
Yeah.
Oh, I see.
Okay.
I was gonna write this so that I can.
Oh, no.
Wait, well, the series.
Okay.
Now you can take those. Right.
This is gonna grow faster.
Approach to zero, which means divergence is.
Right. We got to that.
Well,
Does that look like? Does, X times even negative with X over 5, that's something that we created before.
Kidding.
Yeah. What else?
And woke up in sweat like.
Pull out that 1/5, it would be 1/5 e to the x. Right? Oh, so doing 1/5. Right. Or that you have
Oh, so
The leader has he's like, you just gotta be comfortable here, okay? That makes it.
So I can ignore.
Right.
Divided. Then it's just one over
It's like
here.
a can of but
Yeah.
it just has a lot of good, has a little stuff and then you can wood it and do it. You know what, Rachel? Not going for it, sorry.
Very good at making up that.
No. She gets it 2 weeks later. I'm still talking to her. I'm like, oh, you got it? Thanks.
No, it was and then it got huge. No, it was once you buy it, it's bad. Once you like download it.
Oh, that might not be.
Like 4 drinks of water, like, hey, come on, drink some water.
It wasn't as cool as
Oh, well, you know, it's a derivative Oh, wait, here we go. So that's 1 over x, so that's 1 over. Oh, wait, well then, you're crazy. What if you get rid of 18? Find it out again.
If that limit to
ln of x over x and shift.
honestly, that was kind of tough to take during the end up like, you know, like one of those.
Yeah, we gotta memorize something.
Yes.
That's what I was gonna do. I was like, you can do it.
I used to like look at what
To get rid of that
I put it back in the same class. Not touch
which makes it a little bit easier to look at.
But I think that's
I sure don't feel like a genius right now. Yeah. Just pull it off.
Just makes it
It's just like, would you rather deal with 100 or 200? I'm glad you didn't. And I'm like, nobody cares.
Why is this one awesome?
Oh, because that's what I had. So I pulled that.
Okay, so now what's happening? This is still disturbing.
But then, so remember, once you add it to the other side, that's right. Alright, well, let me correct
You
that.
did something wrong.
That's right.
Or I did.
Or is this us?
Yeah, the integral of e to the x. I'll do that. But
No, the integral of UDX just. But
oh
X.
yeah, yeah.
Here, let's just try to. Got a question.
You want these to be really awesome.
Right?
So it's why negative x? Would it be x, e x, e negative x?
No, it's you. It's you. You take the derivative.
Oh, I get what you're doing. Oh, okay. I just got that.
Oh,
I always have to draw the arrows. I keep looking at somebody else when he walks by because he's not wearing the map. Throwing you off.
I had 2 of those, by the way. I feel like I need to.
You got 2 of those?
Yes, I have 2.
That's how he wears them every day.
Yeah, I get you to
And they're all busted up and they don't make them anymore, so that's why I had 2. But it's not the same dirty hoodie I wear every day.
There's a teacher website that has like really cool math and science stuff for like all these different subjects.
What's it called? Okay. I'm not a huge fan of like math shirts.
In my history.
I think they're all really lame. It's like, what did 0 say to 8? Nice belt.
Like this one,
It's
I
not
like
really a
that.
math joke.
Yeah, yeah, no, that's fair. Like the geology jokes where it's like, don't take life for granted, even though it's vicious. Clearly a middle school teacher. I mean, I laugh.
Reminds you of that big, do you watch Big Bang Theory?
Yeah.
That episode with, what's that, Brian Posehn?
Uh-huh.
He's like singing, they're singing that Indiana Jones
Yeah.
song.
So the integral of even
Sorry, I'm now asking for the website.
I was gonna say,
I,
we know where to go.
you have lost
For the last day.
Yep.
Or.
I almost got a coffee cup like two of my math students.
That's what I got. Okay.
Math teachers are people who help you solve problems you wouldn't have without them.
I'm waiting for like this class, or math class to become antiquated once we're a little more accepting of computers in our lives,
Oh, yeah.
because they're really not going
I was
anywhere.
gonna say, I haven't seen a textbook.
I spend so much time staring at a screen.
Does it just
doing
go to
homework, I love
division?
paper text.
The limit of each, if we look at what the terms do as a sequence, not a series, the terms do approach 0, but remember, it's not enough to guarantee convergence.
You were right, we should.
Because they were already at
You get negative infinity over zero.
Well, okay, so I am gonna have this home, I'll try to reevaluate.
You know, you can't tell me just that.
That is kind of.
Right, like, can you imagine, like, you gotta rock.
I think most people are attempting the integral test on this, is what I gather.
I wish it just tells the answer so I can- Does it go to infinity?
What, the integral?
Yeah.
No, it converges.
Oh, right, because this is 1 over. You're right. Well, like, when you get them in, it'll be 1 over.
What about the infinity part?
They're not, it's not actually.
No, but we plug in E, we get
Yeah, but this is, you can rewrite this.
like the rare one
So this will go 0, so we're left on blank.
They only sell leggings, no t-shirts, so unless you wanna rock
Oh,
some
score.
calculus leggings. But they do have like Converse, like shoes that have like Google Maps up on it.
Oh, nice.
Cruise bags that go, just, you know.
Cruise bag.
Groove, like GROV.
Probably forget.
That's
Trying
fair.
to log it away.
This would be negative
Yeah, where did you
2 over E
find?
minus 2 over E.
Because I think you did the thing that I said. but the one
Okay, so
thing
that's
take it
that's
out,
minus the
divide it
integral
by
of
one
v
fifth,
du, so
it's
minus
five.
the minus 5 turns into a plus 5.
He didn't take out the
Okay.
So that's why that 5 is there.
So it's 2 over E.
That makes sense.
Probably could you do that
I just hate that she's
No. So if we remember, if we compare the k over e to the k over 5 versus this, it doesn't make a difference because that 7 is just multiplying the entire series. That does not affect convergence. There's nothing wrong if you included the 7 in there. The test is still going to be this. You're going to conclude the same thing anyone else would conclude. We have that.
Cody,
plus-
could I ask you a question?
Sure.
Could you technically turn that e to the negative x over 5 to e to the negative x over, or e to the negative x times e to the negative 1? Hold up.
Say that again, e to the negative x.
Over 5. Yeah, and then multiply that times e to the. Or
No, he's saying e to the negative x times e to the negative, e to the,
negative 1/5.
So positive 1/5.
Yeah, possible.
Yeah.
Sorry. Can you do that?
No,
Then-
well, so when we multiply, let me get clear to this. That's not what you were saying. When you multiply these two things, what do you do with their exponents? You add them. Yeah. So you can say it's e to the negative x to the 1/5, or e to the 1/5 to the x, negative x, or some combination thereof.
Oh, crap. Oh,
It was a great idea.
So again, integrating this, we get what, e to the negative x over 5 divided by negative 1/5, so times that negative 25. Sorry, we started at 1. If you had the 7 in there, then you would have negative 35 and negative 25 times 7. Do y'all have any questions on that? Okay.
Oh. Okay, so.
Let's go here. There's f of b minus f of a. We plug in 1, so what do we get? Negative 5. E to the negative 1/5 minus 25. So really, all of this stuff right here is finite. We really don't care about its value. We just know that it is finite. So it's capital N, whatever it is. We just have to address what happens to these two things as b approaches infinity.
Can you scroll up like 2 seconds?
So then we can use growth rates here. As b approaches infinity, what do these two limits approach? Yeah, e to this power grows faster than x to the first power, or x to any power, rather. Yeah, or you can do L'Hopital's rule. Hopefully, clearly, the negative 25 over e to the infinity over 5 goes to 0.
Should that be a b? Negative 5b.
Yeah, if it's up top, we put it down below.
Negative 5x. That should be negative 5b.
Oh, yeah. That's what I'm saying. Thank you. We plugged the b in for the x, so it should be minus 5b. Growth rates tell us that goes to 0. Standard limit stuff tell us that goes to 0. So we have 0 minus some finite number, which means that the integral itself is finite. So therefore, what we know now is the thing we've chosen to compare to is convergent, right? Any questions on that?
Integration by parts.
Would be 30, right? Just took a picture. There it is. Is equal to 30. Yeah, using because this is when I plugged it in, so it's true down, I just let it. So we could now we know.
Yeah, we just have to know. You don't have to know what.
It might be easier.
Just like.
So then,
Okay, so we're not done though, right?
then that means
Step two.
Step 2 is we have to compute the limit. We're going to compute the limit of A given over B, which we now know.
I thought you were just saying,
So we had A was 7k plus 100 over e to the k over 5 minus 70 times the reciprocal of B, which we chose to be k over e to the k over 5. So here's the reciprocal of B. And so again, we're thinking about this in terms of leading term in the numerator, leading term in the denominator. So the leading term in the numerator is 7 e to the k over 5 times k. And same thing in the bottom, we've got e to the k over 5 times k. So the limit equals, well, some of you, so here's the difference between the series I chose and the series that some of you all chose. So some of you all chose the 7k over e to the 5k as b. So the only difference in our computations, yours would be 1. The one that I've chosen though would be what? 7, right? Yeah, exactly. It does not affect the conclusion of the limit comparison test, whether this is 1 or whether it's 7. It's a finite number that's not 0, so both series do the same thing. Yeah.
So all of these were technically multiplied by the same fraction's reciprocal, so aren't they all going to be a finite number?
No. I'll try to think of an example of that just to show.
Yeah,
But
that's
no,
all I mean. I just wanted to know
that's
if
why
that-
these other conditions are present here as well, because it's not always a finite number. I'll find one for after break.
Okay. That's all. All the ones we've done, you just kind of pick the reciprocal.
That wasn't too bad. We definitely screwed up.
So we were like on the right track.
Exactly, yeah.
We would have gotten closer.
they do exist.
You really got the one. Yeah, it's just we're trying to simplify it.
Yeah. We're just trying to do that. It's a whole nother problem.
No, it's
Okay, any questions on that example? All right, and then I have a summary of our tests up to this point. Let's take a break and then we have just one more question here. We'll do that one after break.
No,
All right.
no, what that means is you originally get.
All right.
Time to start class. All right. So this, don't hate me with it. We did this a long way, but I guess the beauty of the limit comparison is we don't have to establish any sort of connection between the A and the B like we did with the direct comparison. So let's look at that same series and choose B sub k to be 1 over k squared. Do we know something about 1 over k squared? What do we know about it? Does it converge or diverge? Yeah, it's gonna what side?
Diverge. No. Converge.
This is what I needed.
It's greater than what it really wants.
Okay.
Well, how did you relate that to
It will, because you're gonna have to put that under X.
So sorry, what was your question?
How did you justify that one over K squared?
It's not.
He's just gonna put it on top.
If this were a direct comparison, if we were using a direct comparison test, it makes a whole lot of sense to choose this series right here as the series we're comparing to, because we have to establish a direct relationship between the chosen and the given. But if we look at the limit comparison test, it just says let A sub k and B sub k be series with positive terms. Other than that, there doesn't have to be a connection between those two series.
So you're saying that you could solve that last one?
Yeah. So then let's see what that looks like.
It's not really usable during direct comparison, actually, something that's relevant.
Yeah. And I'll show you another example where you might have to you have to be careful. So when we compute that limit as k goes to infinity, that's a times 1 over b. So it's 7k plus 100 and that stuff. Times k squared over 1. So what would that limit be? Leading term up top. Leading term on bottom. And what does that limit approach? 0. How do we know? Yeah, exponentials grow faster than powers of k or x or whatever. So there's an example of when our limit's 0. When it's 0, the given series has to converge to tell us anything. So the limit is 0, and b sub k converges. That means a sub k converges.
But what's it converge to?
We don't know. That's the geometric. We know what it converges to. Telescoping, we know what it converges to. Integral test doesn't always converge to the actual value of the integral. The integral test just tells us if it converges or diverges. So really, what is there? I think I'm missing one, but there's those two, geometric and telescoping, we know what they converge to because we have formulas for their partial sums. And the p series, we don't know what it converges to. We know it converges though. So yeah, geometric, telescoping, and p series. Those are the 3 easy ones to determine convergence. Like I said, geometric and telescoping, we have formulas for the nth partial sums, so we can determine exactly what they converge to. P-series and every other test, no, we don't know what it converges to. The best we can do is say it converges.
What are they for then? Like, what are those tests good for if you can't get to the value that they converge to?
So, granted, a lot of these tests that we use are not useful to us when we move into chapter 11. Really, when we move into chapter 11, we're only taking 2 tests from all of chapter 10. And we're taking 2 tests that we haven't talked about yet.
What did we get?
Chapter 11. Yes, Taylor series, Power series, and Taylor series, Maclaurin series. So let me finish this before I lose my place. So the limit is 0 and b sub k converges. Therefore, the given series converges.
Yeah, I haven't seen
As far as all of these other tests that only tell us whether something converges or diverges, like I said, they're not very useful to us. In other senses, maybe these series represent some sort of application problem. I know geometric series are way more common to represent in an application. Like, there's some really cool applications in the textbook for geometric series. Like there's a problem where you stack bubbles on top of each other, where the radii of each bubble diminishes according to a geometric series. Like overlapping objects like dominoes or cards is a geometric series. In series like k7 plus k plus 100 over e to the k over 5 minus 70, I'm really not sure where that would actually show up as an application. So convergence for two particular things we care about moving into functional stuff. Let's look at another one here, just with the same series. And this time let's choose the v sub k series to be k equal 1 to infinity, 1 over 2 to the k. I've seen this series before. This converges. Geometric, right? So now let's check out what happens when we compute this limit. So what would that limit be? Right, and then so that limit equals what as k approaches infinity? What grows faster? Or e to the k over 5. We know e is a larger base, right? But it's divided by 5, so how does that affect the power?
Once you just
Okay, so so if that's what you chose, now you're in a predicament. Now we're just kind of guessing. Well, I think e grows faster because it's a larger base, but the power is divided by 5, right? So we're just guessing. Let's take the guesswork out of it and not choose 2 over k, 1 over 2 to the k rather. Let's choose something that's clearly that makes things perfectly clear. Which one of those grows faster? Okay, so this limit is so the limit is infinity, but if the limit is infinity, we have to make sure that the chosen series diverges. If the limit is infinity and the chosen series diverges, then a sub k diverges. Therefore, that is inconclusive. But now we've seen 2 examples, one's 0 and one's infinity. So there's 2 examples of when it's not. As long as we're choosing things comparable in the vein of what do the end terms look like, then yeah, you should always come up with a finite number.
So with the integral test, since we're choosing a function that's similar to that. Why wouldn't, if we take an integral of that, why wouldn't we just take the integral of the original?
Because the constants barely matter. So why wouldn't we just take the integral of the first one?
The integral of the first one, what do you mean? What's the,
Like the big look.
Of the original function, the sum set.
oh, yeah, this one.
Yeah.
Yeah, you can. But then that's not as straightforward as an integration by parts anymore. I mean, maybe you could try that. I haven't worked it out, but it would still probably work as integration by parts, except for now your functions are a little bit more involved than just k and e to the k over 5. But you can certainly use an integral test on this.
Can you explain that again, why it's inconclusive?
Because the limit is infinite, which means that the top function is growing faster, right? So the top function was this thing right here. So this thing is growing faster. Let's make sure that's true. If the limit is infinity, then a sub k grows faster than a sub k. Yeah, so a sub k grows faster than 1 over 100 to the k. And so we've got a series 7 plus k over 100, etc., that grows faster than a convergent series. So the series that we've chosen is convergent, and the series that we're testing grows faster than a convergent series. So that's kind of like an analogy to the comparison test. When you've got a series that's less than a divergent series, it could still diverge, right? So we've got a series that's growing faster than a convergent series. Just because it grows faster than a convergent series doesn't mean it still couldn't converge, but it could also diverge. So it's inconclusive.
We're using what we worked on.
Yeah, yeah, it's a very comparable analogy to the limit comparison test. And so if that's where we started out, then that's fine. We could default back to our sum being 1 over k squared, or k over e to the k over 5, or something else, and still come up with a conclusion. So it's not that like if this test is inconclusive, we have to just throw it away. We just reformulate what we choose for b. But in the direct comparison test, if it's inconclusive, then typically we move on to a different test. I hope that makes sense. Do y'all have any questions?
I know I have questions, but
Yeah, yeah. The unknown unknowns. Okay. So how about the last series here, k to the 8th over k to the 11th plus 3? So just start with the divergence test. What would the divergence test tell us? The divergence test doesn't tell us anything. Do what?
You might say it's a good sign, so it might be
Yeah, we can say that. Not geometric, not telescoping. Do we want to integrate that? Or can we integrate that? How would we integrate? The derivative of the bottom is 11k to the 10th. We have a k to the 8th on the top. This isn't an irreducible quadratic. It's not a simple linear. Partial fractions wouldn't work. We could try, integration by parts, but I don't know that. I don't wanna do that.
1 over
1 over
k to the third.
k to the third
Yeah.
in preparation for.
In preparation for the section a lot of.
Yeah. So let's try one of those comparison tests. Which comparison test do you want to try? Huh? Limit comparison test? So the chosen series, b sub k, something comparable to that, it's comparable to k to the 8th over k to the 11th, which is 1 over k cubed. The series 1 over k cubed, converge or diverge? Yeah, converges. All right, so our chosen series converges, and we'll just compute the limit. So our limit comes out to be 1, which means what's true about our given series? It converges. Finite limit that's non-zero, both series do the same thing. So the given series, k to the 8th over k to the 11th plus 3 converges as well. Yeah.
You don't have to pick a piece of cake that's comparable, do we?
No, we don't have to pick a b sub, if we're using the limit comparison test, you do not have to pick a b sub k that's comparable. We saw that in the last 2 examples where we chose 1 over n squared and 1 over 100. Sorry, 1 over k squared and 1 over 100.
Is there a reason why you want to take one over the other, like limits comparable or random one?
No, I don't think so.
Generally, just take one that's more comparable.
Yeah, right. Not with the limit comparison. It doesn't really matter the relationship between A and B. Again, what you could end up running into that last situation where we had this, where it was inconclusive. But again, if you're in that situation, you would just choose another series.
Yeah, it seems like it gives you a little like hierarchy or something, at least that makes sense.
Right. Yeah, and it's more flexible than the direct comparison test. Okay. Any other questions?
Are we gonna have to worry about doing like really difficult
In the homework or?
No, for the
Yeah.
like we'll be needing spare code for.
You ran intensely difficult.
Yeah, I don't know. It's a relative
Will
term.
like take a page or will?
It depends on how big you're writing. I don't really know how to answer that. I mean, because honestly, when I look at our class notes and our homework and our exams, I think our class notes and the exams are easier in a lot of senses than the homework is.
Yeah.
I don't know about y'all, but if you look at our class notes versus our homework versus our exams, I think you can get a good sense of the kinds of things I put on the exam. All right, so like I said, we're deviating from the schedule in the syllabus. Instead of going directly into 10.7, we are going to go in order and talk about 10.6. So in 10.6, we're looking at the alternating series test. How do we handle alternating series? All of the tests we've seen up to this point have said we've got series with positive terms. So here's now series that don't have all positive terms. The first series we're going to look at is the alternating harmonic series. Remember, we looked at the harmonic series via the integral test and said that the harmonic series diverges. And we'll look at now the alternating harmonic series. So let's just write out the first four terms of the alternating harmonic series. What would they be? The first term is 1. The second term is -1/2 plus a third minus a fourth plus a fifth minus a sixth, etc. Okay, so that's our alternating harmonic series. Find the first four partial sums. We can do that, but we're kind of pressed for time. So if you want to do that, feel free. This is what we're going to use to justify this reasoning, anyways, behind the alternating harmonic series. So here's the alternating harmonic series plotted with the sequence plotter. But as we'll see here, this is the first term. Here's our second term. This is our third, this is our fourth, and so on and so on. What we see is, visually, it looks like it's converging to a specific value, via oscillations. But if we kind of look at those as separate, the even terms versus the odd terms, this is our justification for the convergence of the alternating harmonic series. So the even terms, not terms, but the even partial sums versus the odd partial sums. Both sequences are non-increasing, non-decreasing, and bounded. So as individual series or partial sums, they converge. So really then, we have to show that they both converge to the same value in order to show that the alternating harmonic series converges. Okay, so we're going to assume that the even partial sums converge to L and the odd partial sums converge to M. This relationship you can verify if you want, but the even partial sum is the odd partial sum minus that even term that we've stopped at. So here a specific example: S sub 4 equals to S sub 3 minus A sub 4. So that's just one specific example. You can verify that's true for all. And then we'll take the limit of that relationship and get L equals to M minus 0. And then that means L equals to M. That means the even terms and the odd terms of the alternating harmonic series both converge to the same thing. So the alternating harmonic series does converge. We're not going to show this, but it's a well-known fact. The alternating harmonic series converges to the natural log of 2. So this, might bring up some questions. When we looked at the alternating harmonic series, we have convergence when the harmonic series itself was divergent. So that notion of a series such as the alternating harmonic and the harmonic, when one converges and one diverges, is also addressed in this section. And it is an important topic that does carry through to the next section and into chapter 11. So there's a few important things included here. but for now, our alternating series test. We've got an alternating series, -1 to the k plus 1 times some a sub k. Alternating series is convergent provided the terms are non-increasing. That means the next term is less than or equal to the previous term, just for some k. So eventually it has to be a non-increasing series. Remember, that's virtually what that means is it's pretty much decreasing. I mean, it can be constant all the way through, but that's really atypical. And so often to test that, it's not clear sometimes when you look at a series if it's decreasing. So we have to default sometimes back to the first derivative test. Just keep that in mind. So if the series are the terms of the series are non-increasing, and the limit as a sub k, the limit of a sub k has to approach 0 as k approaches infinity. Otherwise, the alternating series test is inconclusive. Now, just be very careful in how we're interpreting this. The terms a sub k that we're looking at are only right here. Notice this test, it doesn't even consider the alternation, is that a word? The alternating part, thanks. Right, so when we talk about a sub k plus 1, we're only talking about the part of the series that doesn't involve that switch. And so that's here as well. And so the note here is there is potential for confusion, because the second item for a series that has positive terms, the second item is just the divergence test. But that's not what this test is in with respect to an alternating series.
Something goes here.
Well, it has to go to 0. The non-alternating portion has to approach 0, and the terms have to be non-increasing. So the potential for confusion is that a series with positive terms, this limit equaling 0 doesn't imply convergence or divergence. That's the divergence test. For an alternating series with non-increasing terms, that does imply convergence. So here, non-increasing, that's condition 1. This is condition 2. So read that and just let it sink in and let me know if you have any questions, because it's very important to distinguish.
Is why a valid question?
Why? Yeah, I mean, maybe if we looked at the proof for these, we could justify why a little bit more carefully.
I mean, obviously, it begs the question, of course, from why wouldn't it? But we saw logically it doesn't work.
Yeah. So for positive terms, the divergence test didn't have this criteria that they have to be decreasing, because that's kind of built into the test. If the divergence test is 0 and the terms are positive, it's implicit that they're decreasing. Okay, so both conditions have to be true for an alternating series to converge. So we in sort of a different way, showed that this alternating harmonic series converges. Let's use the actual alternating series test to show that it converges again. So the first thing we want to note is that a sub k is everything but the alternating part. So our a sub k is just the 1 over k. So is a sub k plus 1 less than or equal to a sub k? In other words, is 1 over k plus 1 less than or equal to 1 over k? Yes. We know it's not equal. It's kind of redundant or not necessary rather to put that. Okay, so first condition of the alternating series test is satisfied. Second test, or second condition rather, we have to look at the limit as k approaches infinity. And for convergence, that limit has to be 0. So the limit as k approaches infinity, 1 over k, certainly equals 0.
We back up for a second.
Yeah.
How did you get 1 over?
Because that's the comparison, because we want to look at the k plus 1 term and compare that to the k term. Because we're looking at the terms way out here. We're saying, is this term less than this term? And if so, as we get out towards this direction, that means that the terms are not increasing. It's non-increasing. Yeah, right. Again, if you don't want to make this comparison here, we could look at the derivative. Which is pretty simple in this case. The derivative is always negative, right? So that is a decreasing, the terms are decreasing. Just because the series is starting at 1. Yeah. So condition 1 and 2 are both satisfied. K plus just k. So we know that alternating series converges. Have any questions on that? Easy enough. It's really everything that we've done up to this point is built into this test with the testing for decreasing and the limit. That's key. The next two examples are these are examples of where the alternating series test would be inconclusive. So this series here, given in example 1, the first criteria, which was non-increasing, this condition fails. Because we see that, again, this is a sequence, not a continuous function. So, we'll probably just want to visualize these discrete points. So although the oscillations do get smaller and smaller, it's still oscillating a little bit. So you have it increasing for a little bit, and then it's decreasing and increasing and decreasing again, right? Well, I mean, even if this were the axis and it was doing this, it's still decreasing, increasing, decreasing, increasing. So. All right, so with that particular series, then the alternating series test is inconclusive. The terms of the series sine k plus 1 over k do approach 0, so it does pass that condition. The second example is where it passes the terms R, non-increasing. But the limit of the a sub k doesn't equal to 0. And again, notice the second condition for any alternating series, it's not the divergence test. The divergence test says we look at the entire series, right? Not just A of k. So if this is an alternating series, with respect to the divergence test, then all of this negative 1 to the k, 1 over k plus 1, all of that is your a sub k in the divergence test. So here's the divergence test right here. We took it all, even the alternating part. And that's going to either be 1 or negative 1, still not 0. So like that series, even though we can't conclude anything from the alternating series test, we can conclude something about it via the divergence test. Just make sure that you're keeping those things separate.
So we wouldn't use the divergence test on this.
We could, because the alternating series test fails, then we could say, well, let me try something else. Let's try the divergence test. It's not 0, so therefore it does diverge.
And right now, the only other test we have is the divergence test.
Right, because all of the other tests were let a sub k be a series of positive terms, right? Any questions? I just wanted to give you a few examples of where it was inconclusive. It's not that we encounter those a lot, if at all, but. I left out some information on this one, so let's just skip this. This thing is so annoying. Okay, let's do the example 3. So give example 3 a shot.
limit?
Yeah. So you can use so I hopefully the second condition is easy to compute, especially if you're thinking about growth rates. Right, K grows faster than ln of K. If you just say that ln K over K is non-increasing, I don't think that's clear. It's not sufficient. So don't just assume that it's non-increasing. If this were an exam problem, you would need something other than, oh, it's non-increasing. It's not good. And what do you mean?
So I realize like ln K, my A of K is ln K over K. Right, so say that is greater than or equal to ln K over K plus 1. That.
So which one's larger?
The ln K over K is larger. Yes.
So does that make sense? Maybe it seems intuitive, maybe it doesn't. I don't know. What's the derivative?
Isn't that false?
Yeah, so we're not a full consensus here. So we look at the derivative of ln K over K. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So there's our rate of change. When does the rate of change equal 0?
So we take the derivative
A of K. Because we want to know is the series or the terms non-increasing. So we just look at the terms themselves. Well, I mean, yeah, it's a valid question. K is ln K over K. So we've got to find where that's 0, right? And then you test here and here, where our sum is from 1 to infinity. Just after some point, it has to be non-increasing. So if this is negative out here, then we've shown that it's a non-increasing series. So we'll maybe have to start there on Thursday. You're not gonna have a graph or anything on the exam, so you've got to be able to justify fully if it's decreasing.
Yeah.